Hi, again, this is the base knowledge for short circuit calculation. We will discuss causes of fault current and transient nature of fault current. Excel formulas for impedance simplification. Let's proceed. We completed base knowledge 1 and 2 in the previous video. If you didn't watch it, please look for it and watch completely for basic understanding. You can repeat it when something is still unclear because repetition is the mother of mastery. Let us now discuss the causes of fault currents, base knowledge number 3. Our first cause is voltage surge. Voltage surge happen in a very short time period, as you can see in the sinusoidal waveform in the figure in your screen. Those surges, if not controlled, is detrimental to our equipment and operation. It can damage insulation, then will result to short circuit. A voltage surge is an increase in electrical voltage in a circuit that is above the normal operating voltage. If the surge is large enough, it can cause the current in the circuit to increase to a level that is higher than the circuit is designed to handle. This can cause the circuit to become overloaded and potentially create a short circuit. We know that a short circuit can cause damage to any electrical devices connected to it, as well as create a fire hazard. It is important to protect against voltage surges to prevent short circuits and the potential damage they can cause. This can be done through the use of surge protector, which are devices that are designed to limit the voltage that is allowed to pass through a circuit. The second cause of fault current is the deterioration of insulation of wires. This is a very common and you need to do frequent inspection of your electrical system, of course, especially those wires with bending tension. Over time, insulation degrades due to several factors like temperature, bending tension, and age of the wire. We need to follow Philippine electrical code related to the bending radius to avoid this problem. Insulation is a layer of material that surrounds electrical wires and helps to prevent electrical current from flowing through unintended path. If insulation of a wire becomes damaged or deteriorates over time, it may become less effective at preventing electrical current from flowing through it. It can lead to a short circuit, as the current may be able to find an unintended path to flow, such as through the insulation itself or through another nearby conductors. The third cause is loose connection. This is common in our electrical system. When there is a loose connection, hot spot is present. When not corrected, hot spot can burn the insulation of nearby wires, and when insulation breaks down, then short circuit is likely to happen. It should be part of your maintenance program to inspect loose connection, or if you are doing electrical audit, look for evidence report that hot spot rectification is done or IR scanning was done twice a year. The fourth cause is accumulation of dust and moisture in electrical equipment. This is another cause of a fault, especially in areas where condensation is high. When an electrical system or electrical equipment is exposed to dust and moisture, short circuit is likely to happen. Electrical inspection should be a system or a normal preventive maintenance process in your company to avoid this scenario. Dust and moisture can accumulate on the surface of an electrical component and inside electrical equipment, such as switchboard and panel boxes. If the dust and moisture are not removed, they can conduct electricity and create a path for electrical current to flow. This can cause a short circuit, as the current may be able to bypass the intended path through the circuit and flow through the dust and moisture instead. The fifth cause is intrusion of metallic or conducting object to light parts of electrical equipment. This is a direct cause of fault that can damage electrical equipment or even take people's lives for those who are working nearby. In my experience, I've seen people maintaining switchgear, later to find out the tools was left inside, and then after energization, explosion happened. The effect was great and escalated. Damaged switchgear, accident to people, and business interruption and loss of income. This scenario can be prevented if procedure is established prior to energization. This incident teaches us a lesson. What you bring during the preventive maintenance, especially tools, came out when preventive maintenance was done. And before energization, huwag tayong magmamadali. Strict safety procedure is needed. The sixth and the last cause is a little odd, but this scenario happened. The presence of rodents or cats. And sometimes snakes. This scenario is totally not a good one. This happened in areas where panels are not commonly visited and panel holes are not properly sealed. With that, those unwanted animals get in and causes problems. This area should be included in your electrical inspection. Please remember those common causes of fault. Okay, in summary, we discussed the 6 major causes of faults. There are lots of things we can do to mitigate those causes and prevent hazards attributed to the use of electricity. What we have learned here are 6 major causes of faults in commercial or industrial settings. There are more, but those that I mentioned are common that cause a short circuit. The next step we will discuss is the transient characteristic of fault current. See you in the next step. The nature of fault currents are basic information we learned in college. For now, let's have a short recall of the information we already know. We will take a look on the transient level of short circuit so that we can have a better appreciation of the values we will compute later for short circuit current. Let us now proceed to understand the fault current characteristic. In a very simple transient level explanation, the figure in your screen shows a symmetrical AC waveform for a current. Number 1 is the middle line or the zero axis of the wave. Number 2 is the envelope of peaks of the sine wave, which is symmetrical above the zero axis. This is the normal waveform of the current in a transient view. The words symmetrical and asymmetrical describe the AC wave above the reference to zero axis and the axis of symmetry. And if the peak of the current wave is same on the lower and upper peak around the zero axis, we called it symmetrical current, as you can see in the screen. And asymmetrical is the other way around. If the envelope of the peak current are not symmetrical above the zero axis, it is called asymmetrical current. It can be a totally offset or a slight offset, as you can see from the figure. This asymmetry is very critical in our study of short circuit. Let us dig deeper. What is it? Now, let us take a look on the oscillation of a typical short circuit. The image in your screen shows that the envelopes of peaks are not symmetrical above zero axis, point 1 and point 2. Remember that short circuit current are always asymmetrical during the first to 5 cycle after the short circuit occur. That's 5/60 or 0.083 seconds. In your screen are values very significant when we study relay settings and protection coordination, and you have to be aware that short circuit happened at that cycle of time. The asymmetrical current is maximum during the first cycle after the short circuit occur, as seen from point 1 and point 2. And it becomes symmetrical in a few cycles after 5 to 8 cycles, point 3 and point 4, as you can see in the screen pointed by the arrows. In the figure in your screen, it shows the oscillogram of a current waveform. The DC component of the fault affect the asymmetry of the current waveform. The asymmetrical component is at maximum at the start of the short circuit current and decays to a steady state value over time due to the reduction of the flux in the machine. The DC component decay also from 1 to 5 cycles and the wave reduced to a steady state from 6 to 8 cycles. You may ask, Sir Bear, what is the significance of knowing this transient characteristic of fault current? That's a very good question. Here's the importance of the transient current contribution of all the dynamic equipment, which are the sources of fault currents, which we will discuss next. Here is my answer. In your screen, you can see the sinusoidal wave of the incoming utility. Next wave is the generator. Third is the synchronous motor. And the fourth is the induction motor. At the instant a fault happened within 5 cycles, those sources of fault has a different response and those sources combine together during a short circuit. It gives you the magnitude of the total fault current wave on the first 5 cycle traveling to the specific point in the electrical system to release the fault current. The graph shows symmetrical. Just like I said before, in actual wave, asymmetrical is the shape. Imagine if those waves are asymmetrical. The first cycle fault, which is colored by light blue, is very significant to study and considered in the design and sizing of kite of protection. Last in the slide shown is the 3 region of short circuit current. The first 1 to 2 cycle is the sub-transient region. The last 3 to 5 cycle is the transient state region. And the third is the steady state region. If you have more time to take a closer look on this oscillograph, you can determine that the XR ratio is higher in the sub-transient region going down to steady state. We have discussed the simple transient nature of short circuit. Let's proceed to Excel formulas of complex numbers that can be applied to impedance simplification in the next steps. See you in the next module. Okay, we have discussed the transient nature of short circuit. Now, we will discuss Excel formulas because we will encounter a lot of data in our single line diagram. One of those data are impedances in complex number, and some operations require polar to rectangular coordinates conversion in order to calculate impedances. Don't worry, Excel software will make our calculation a lot easier. It's a powerful tool to compute manually the impedances of an electrical system if you don't have an ETAP yet. The slide shows us the basic formula we will use for impedance simplification. We will apply Excel formulas for series and parallel impedances. I hope everyone recall this formula in our Circuit 1 and Circuit 2 subjects. With complex number involved in impedance simplification, this formula of complex number is useful because the concept of addition and division will be used a lot here. Let us use Excel for complex number. I have here a sample of Excel file, a resistance R of 2 from column A, a reactance of X of 1.5 ohms from column B, solve for impedance Z. To translate it to complex number using Excel, the formula is equals complex, close quantity, move cursor to A3, then comma, cursor to B3, comma, then choose J or I operator, then close quantity. Then you have a complex number of 2 plus 1.5J. Remember that you have to be consistent with J operator or I operator under double quotation. For complex number, when you use J, use it in the entire calculation and don't mix up, okay? To solve for impedance 1 over Z, to translate it to complex number using Excel, the formula is, see the point finger, equals IMDiv, open quantity, type 1, then comma, move cursor to C3, where you have the impedance C, close quantity, enter. Then you have a complex number of 0.32 minus 0.24J. For a series impedances Z1, Z2, Z3, we need to add all those impedances. As you can see from column B, we have 3 impedances. To find the total impedance, we need to add everything. Our Excel formula is, with pointed fingers, equal IM sum, open quantity, choose D3, D4, D5, close quantity, enter. You will get 12 plus 10.5J. If we want to add a parallel impedances Z1, Z2, Z3, we have to do the inverse 1 over C of the impedance first before adding them. I've done it in column E. Just type equals IMDiv, open quantity, D3 so that you can do the inverse. Once all the impedances is done with the inverse, we can now add the impedances. The Excel formula is equals IM sum, open quantity, move your cursor to E3, E4, E5, close quantity, enter. We have a value of 0.55215 minus 0.44691J. We need to inverse it to get the impedance CE. To do that, let's use the Excel formula equals IMDiv, open quantity, type 1, move the cursor to E8, close quantity, enter. We've got 1.0942 plus 0.88565J. Now to get the absolute value of that impedance, we can use the formula equals IM abs, open quantity, move the cursor to E10, the impedance, close quantity, enter. We've got the value of 1.4077 ohms. You can just copy the R value and the X value, but you can see we have Excel formula for that also. We can use equals IM real E10 as you can see from the screen. For the reactance, the Excel formula is equals imaginary, open quantity E10, close quantity, enter. If you want to know the angle in degrees of the impedance, the Excel formula is equals degrees, open quantity, IM argument, open quantity E10, close quantity, and close quantity, enter. You've got the angle 38.98 degrees. Now we have an exercise for you to use the Excel formula to finding total impedances. You can download the exercise impedance calculation using Excel in our group chat. I already posted the Excel file there. Actually, in my workshop, I just only give 9 minutes for impedance calculation, practice, and CR and coffee break. Okay? And actually, I give some timer if I want to time them. Okay? Okay, I'll do the sample for you to start and I will compute for the impedance. Next, you will compute the remaining and we will check it together. So, madali lang, parang ganun. I have here a simple impedance diagram of an electrical system. As shown are utility impedance ZU, transformer impedance T1, cable impedance Z1 to C4, and motor impedances M1 to M3. You will compute for the following. Compute for the following equivalent impedance, as you can see from your screen, C equivalent 1 to C equivalent 4. All equivalent impedances are in series. Use the series Excel formula. But the total impedance of the system in reference to bus 1 is the parallel of the impedance Z equivalent 1 and C equivalent 5. To find the total impedances, you need to find C equivalent 5 first, which is parallel to C equivalent 2, Z equivalent 3, and Z equivalent 4. You can download the file that already in our group chat, and I'll do the first calculation solving the impedance during our discussion, and you can watch some of my calculation here in YouTube. Then you will calculate the remaining impedances. That's my assignment. Okay, this will be the next topic. So see you in the next video.